Let me continue now with the same drawing sheet. It doesn't matter, but now I will do something which is called the WKB approximation. This is a classical thing. I will show it in a simple case, and you will see that it is sort of related to what we were doing with the Matthew equation. So I will do it by example. Okay, so let's take an example. Let us look at this equation. X double dot plus t cube x equals 0. So you see we have a time varying coefficient linear equation. For t greater than 0 we expect oscillatory solutions but not harmonic. And for t much bigger than 1 we expect rapid oscillations, very fast. This we may expect, but what do they look like? So let us go to MATLAB and make a new file, and we will call this one that, and we will say x dot is equal to x2 and minus t cube times x1. So you see that that is our equation. Okay, I am interested in positive t. For negative t the solution nature is different. You can experiment, but we will not do that here. OP equals, because I just cleared everything, that is why I have to do it again. I will say t x equals ODE 45, and then I will say WKB APP, and then I will say from, let us say 3 to 20, and let us use initial conditions 1, 0. Three to 20 is a bit high, and that OP is a bit tight, but it's worked out. So we have t x1, and that's the solution. So you can see that it is decaying in magnitude slowly, not exponentially, and it's oscillatory, and it gets faster and faster and faster. Okay, so there is a nice approximation for this kind of solution, and that approximation also helps you think about oscillations. So this is an oscillation where in place of a constant stiffness or in place of a periodically varying stiffness, you have basically a very large rapidly varying increasing stiffness. Okay, so this is some problem, and then we will study this. So the key to study this is to note that if we had x double dot plus omega square x equals 0, we would have x is something like a sine omega t plus b cos omega t. So over here, if we think of this as somehow corresponding to omega square, then omega is something like t to the 3 by 2. Omega t is then t to the power 5 by 2, but that's not what we want. We actually want, if this is omega, what we want is the integral of omega dt. If omega is constant, that is omega t. So this is the one that works out. And so t to the 3 by 2 gives you 2/5 of t to the power 5 by 2. Okay, so this is the correct clock as it happens for this oscillation. All right, so now here is what I will do. I will say tau, my clock, tau is equal to 2/5 t to the power 5/2. This means t is equal to 5/2 tau to the power 2/5. Okay? Both are true. Alright? Good. Now let us go to Maple. So let's start over here. No, that's not what I want. I'll get rid of that and say t cube times x of t, just to remind you that that is what we want. Then I will say I will change this now, right? So what I want is, I want to say x dot is equal to diff x of tau with respect to tau times the derivative of tau with respect to t. So I have to define what tau is, and tau is 5/2 tau, 2/5 t to the 5/2. So let me say tau equals 2/5 times t to the power 5/2. Okay, so this is x dot. Why did that not work? Oh, I see. I should call this tau 1 just so that it doesn't get confused. Okay, so then I should write here tau 1 and then it will work. Okay, so that's x dot. Alright, now I have to get x double dot, and I'll do x double dot is equal to diff x dot with respect to t, and that will give me this part, plus diff x dot with respect to tau times diff tau 1 t. Okay, so I hope you'll work through that and see that that is correct. Okay, so now that is x double dot, and then I have dEA is equal to x double dot plus t cube times, only this x is now treated as function of tau. Okay, so this is my differential equation. I still have to solve for t. Okay, so I solve for t. How do I solve for t? I have t here. T is 5/2 tau to the power 2/5. Okay, so I go dEA is equal to, substitute t equals 5/2 times tau to the power 2/5 in dEA. Okay, so now I've got this strange sort of differential equation, but that's okay. Now I say dEB is equal to, and I have this one here, minus solve dEA for the same thing. Okay, all right. This is getting to be a bit of a problem, but that's better. Okay. Okay, very good. Now I hope you realize how wonderful this is, that this has become basically like a harmonic oscillator, only here is this thing that looks like a damping term, and it is 3/5 times 1 by tau. Okay, so now I'm going to play another trick. So this leads to, let me write with green here. So I have x double prime of tau plus, and if I remember correctly, 3 by 5 tau x prime of tau plus x of tau equals 0. I hope you agree that this is easier than the previous one in some way. You know, it's like for large tau you can see that this term is going to be small, and it's almost like a harmonic oscillator, and therefore this is the oscillation time scale. Okay, but we have to do something with this as well. So what I had done for the Matthew equation, remember I had 2cx dot and I put e to the power minus c t. This again is not c times t, it is the integral of c dt. Okay, so this 2 has to come out, so I have 3 by 10 tau. Then let me do d tau d tau and integrate, which is 3 by 10 log tau. Okay, so then I say e to the power minus 3 by 10 log tau is equal to e to the 3 by 10 log 1 by tau, which is equal to 10, which is equal to 1 by tau to the power 3/10. And so I will now say x of tau is equal to 1 by tau to the power 3/10 times y of tau. Okay, this is very classical. You can just learn this method. Okay, so I come here and I say DEB is equal to the previous. Then I say XS is x of tau is equal to 1 by tau to the power 3 by 10 times y of tau. Okay, then I say DEC is equal to expand, substitute XS DEB. Okay, so I've done that, and now I solve for this. So I say DEC is equal to Control V minus solve DEC for the same. That's my new differential equation. Okay, very good, and I hope you will agree that this is very simple. Let me expand it and you will see why it is simple. We are interested in large tau. So if tau is large, 21 by 100 tau square is small compared to 1. Okay, and therefore for large tau we will drop this, and y is going to be a sine tau plus b cos tau. Okay, so we will come here and we say y is a sine tau plus b cos tau, which means x is 1 by tau to the power 3/10 a sine tau plus b cos tau. That's the approximate solution. What is tau? Let us remember what tau is. Tau is 2/5 t to the 5 halves. So let's come here to our MATLAB window and we will say tau is equal to 2/5 times t dot power 5/2, and then I will say x approximate is equal to, I'll just use 1/tau to the power 3/10 dot star sine of tau. The cosine is there and things like that, but we don't have to worry. This is good enough. And so now we can plot the two and you can see whether the solutions are similar. I should multiply by something and shift the phase a bit, that's all. Right? So how much should I shift the phase? I should shift the phase by about pi/2. That means I should just make this a cosine. That will be good enough. And I should multiply by about 1.8. So that will give us a reasonable match. You can see that the asymptotic is really good. It seems to be slightly bigger. That is because I need to use a better scaling. It's, I have to use slightly different initial condition, right? So it's really a very good match, and we will end the matter there. Now that became very slightly smaller. Okay, so you can see that the match is good. This is the match. That's the WKB approximation. I'll give you an assignment on this as well. Thank you.